because we're going to utilize them. All right. They're actually theorems. You can prove these results. Now these results hold regardless of the type of random variable we have. That is, it holds when we have a discrete random variable, and it holds when we have a continuous random variable. Now we don't talk about the computation of the mean or the variance for a continuous random variable in this class because it involves techniques involving calculus. So when we talk about a continuous random variable, I have to give you what mu and sigma are. The mean and the standard deviation of our random variable. Nonetheless, these rules hold in either cases. Now let's take a look at the left sides and then the right sides. On the left side for this first equation here, I have the Greek letter mu. Generally speaking, the Greek letter mu always refers to the mean of a random variable, theoretical mean, all right? Defined for a discrete random variable, as I gave you in the overheads, and defined by techniques of calculus when you have a continuous random variable. Now the subscript here, you see a little letter A, a little letter B, and a capital X. Now capital X refers to a random variable. This whole thing is a random variable, or is used to represent a random variable, whose value, or what we observe, is something like constant A, a fixed number, plus another constant B times the results, or the value I observe for X. In the previous overhead, I used the symbol Y for this algebraic statement. So I could have over here the mean of Y is equal to this when Y is defined by this expression. Now, the mean of that new random variable is in fact simply the constant A plus the constant B times the mean of the random variable X. So let me illustrate that. Suppose I have a random variable X, and we abbreviate random variables sometimes by doing R period, B period, or just RB. We have a random variable X, and let's assume that its mean value, say, is equal to 5. And I'm going to assume further, although I won't use it initially, that the random variable X has a standard deviation or a variance. Let me pull out a new one here. All right, now suppose I construct a new random variable where I'm using the symbol Y. Suppose I make that 5 plus 3/2 times X. This is my A. This is my B. What is the mean of the random variable Y? Well, the mean of the random variable Y is defined, well, Y you see is nothing more than 5 plus 3/2 times X. Now the rule says all I to do is take the constant 5, my A, add to it 3/2 times the mean of x, and I've told you the mean of x is 5, so that would be 5 plus 3/2 times 5, and when I work out the details, let's see, 3/2, that's going to be 7.5, so this is going to be 12.5. This result holds whether x is discrete or whether it's continuous. All right, now, that's an application of that rule there. Let's do another, or let's look at the next two rules.
The formula doesn't release a standard deviation,
Well, I'll use this information in a little bit, okay?
later on.
Later on.
Okay.
Suppose I have two random variables. Let's call them x and y. And I'm going to create a table, something like the author does, and in some of the problems. X, say, has a mean of, say, 7, and y has a mean of, say, 11.5. Sigma for x is, say, 4.1, and sigma for y is, say, 6.2. Now, I'll use these values when we get to another overhead. Now, I can create a new random variable w, which is either the sum of these two random variables, or I could take their difference. Now, this rule says the following. The mean of w, which according to that equation there is simply the sum of the results of x and y. The rule says all I have to do is add the means for x and y. So that would be equal to 7 plus 11.5. Which, when added together, I guess that's going to be, what, 18.5? Now, what would be the mean of the difference of x and y? Well, that would be the difference of their means. And that would be then 7 minus 11.5. And that would be then equal to a negative 4.5. Okay, so I've illustrated each one of these rules here. You can have a mean which is negative. There's nothing that rules that out. Typically, most of what we do in stat classes, the means will be positive, but it need not be that way. All right, now, these rules here are the same rules I have here, except I'm using expectation notation. When you see the word E, this is what's sometimes called expectation notation. It's the same set of rules, and the author uses, I think, while he uses both, the expected value of a sum of a constant plus another constant b times x. That is the constant a plus b times the expected value of x. There should be a multiplication symbol in there, or it's understood. This is perfectly reasonable in math not to have a multiplication symbol there, it's understood. But I'm taking b times the expected value x. Well, you see this notation here is the same thing as mu of a plus b times capital X. And this is the same thing as a plus b times the mean value x. This means that. This means that. Or just a different way of expressing the same idea. Okay. Now, let's take a look at this notation here involving variances. On the left-hand side, we see, well, first of all, we have three equations. Let's look at the first one. I have the Greek letter sigma. Anytime you see the letter sigma, sigma is the symbol we use for the standard deviation of a random variable. The relationship between the standard deviation of a random variable and the variance is straightforward. You take the square root of the variance to get the standard deviation. So if I represent a variance by sigma squared, well, I represent the standard deviation just by sigma. Okay? Now, these rules apply to variances, not to standard deviations. So in the text, what you need to do when you have a problem that will involve one of these rules, you want to make sure you're dealing with the variances. Apply your rules in terms of variances, and then take the square root to get the standard deviation. All right, let's take a look at this here. On the left-hand side, we have the symbol, a sigma, the Greek letter sigma. We have a subscript of a plus bx. It's understood here that a and b are constants, and my random variable is x. I'm creating a new one using this formula. Now this 2 in the upper right-hand corner is an exponent. I'm squaring something. That's what I'm using to represent the variance. Now on the left-hand side, I'm saying this is a symbol that represents the variance of the random variable a plus b times x. A and b are considered or assumed to be constant numbers, and x is a random variable. On the right-hand side, you see the symbol b, and it's squared, and we're multiplying it times the variance of x. Again, there's no multiplication symbol there, but it's understood.
Why is your A?
It does not influence the variance. That's the punchline here. If you add the same number to all your numbers, the variance is not going to change.
But B is.
But B will affect the variance because you're scaling some value. Not quite the slope, but you're scaling it. In a way, it is. But we're just, B is what we multiply x times. A is that we shift every value by the same amount. So the variance, which is a measure of how things are dispersed about the center of the mean, is not affected by A. So over here, what is the variance of 5 plus 3 halves times x? Well, I take 3 halves, I square that, and I multiply that times then the variance of x squared. This would then be, squaring this would be 9/4 Now, sigma squared is 3. So the variance of this new random variable is going to be 27. 3 times 9 is 27 over 4. And what does that make then the standard deviation? I take the square root of all. So the variance of, the standard deviation of 5 plus 3 halves times x is in fact the square root of all that. And this would be 3 radical 3 over 2. If you want a decimal approximation, you can do that on your calculator. Okay. So what I've done is I've applied this rule here, and A in no way influences the variance, and consequently no way influences the standard deviation. Now, the next rule is a rule made under the assumption that x and y are independent. What does it mean when they're independent? Well, I think the analogy I used last time is if I have 2 dice and I roll them, let's assume they're fair 6-sided dice, and the numbers I can observe are 1 through 6. What happens on one die doesn't help me in any way better understand what happens on the other. They are independent. Okay, now, when that is the case, this rule here holds. The variance of the sum of 2 random variables which are independent is nothing more than the sum of the variances of the random variables x and y by themselves. So over here, in this case, what is, let's see, I defined, I think I said w is equal to x plus y. What's the variance of w? Well, w is nothing more than the sum of x and y. Now let's assume that x and y are independent. That's the variance of x plus the variance of y. So here I'm assuming x and y are independent. So the variance in the new random variable w is 4.1 squared plus 6.2 squared. And if I whip out my calculator, in this case, .1 squared is equal to 16.81. 6.2 squared is equal to 38.44. The sum of these two numbers would be this is going to be 5.25. Now, what is the variance, or excuse me, what is the standard deviation of W? It'd be the square root of that. So the variance of W, which is the variance of the sum of X and Y, excuse me, the standard deviation of W, the standard deviation of X plus Y, because that's how we define W, is the square root of that 55.25. Now if I take the square root of that 55.25, I get the following: 7.433 and so forth. You will note that that is not the sum of these two values. This value here is not simply the sum of these two values here. Because sometimes students will think, oh, the square root of a squared plus b squared, oh, that must be the square root of a squared plus the square root of b squared, and that must be equal to a plus b. That's false. That's not true. It is the case. The square root of a squared times b squared. If this, instead of being addition, this is multiplication, that is the square root of a squared times the square root of b squared. That is true, this is false. This is what we use in statistics. We almost never use that. So it's a sum that we need to figure out, and this rule does not apply. This rule is true, it's just not applicable in this circumstance. Okay. Now, I think this was probably the last part I got to. Whether I add or take the difference of two independent random variables, the variance is the same. That is, the variance of a difference is still the sum of their individual variances when x and y are independent. Seems a little strange, but that's because they are independent. Now, we don't use this so much here in this class, although we use it in subsequent in 244. Now, if we have two random variables which are not independent, these rules have to be replaced by a more general statement. Okay? But we don't, generally speaking, go there in this, either in 243 or in 244. But you could have those circumstances, but the rules have to be, they're more general than this. If they're not independent, then you have a third term involving the Greek letter rho, which is their theoretical correlation coefficient. You may remember R. R and rho are related. R is the observed value, rho is the theoretical value, but we don't make use of that either in 243 or 244. All right. These are the same rules, but expressed in terms of the VAR notation. Let's see here. Random variables, as I've indicated before, are often represented, or we use the symbol RV, all right, to stand for random variables. It's not recreational vehicles. All right. If we use a capital letter X to represent a random variable, then a specific value is often represented by a small letter x. And I did that in the expectation notation. Capital X is the process or the thing that we observe and take on multiple values. Little x is the specific value. Now, why are we interested in such things as expected value of a random variable or the mean random of a random variable? Well, if we go out and collect data, in any of the examples we've discussed, for example, in the rolling of a die, suppose I take a die and I roll it, say, 1,000 times. I add the number on the top face and I add them together and I divide by 1,000. Well, the result will be very close to the mean value for a random variable. I don't know if I did this last time. What's the mean? In fact, we should probably do that. Let's stop for a moment here. I've got suppose X is the number of dots on the top face of a fair six-sided die. X can take on the values 1 through 6. The probability of each one of these is 1/6. So to 5 decimal places, it's that value there. What is the mean value of X, or the expected value of X? Turns out to be 3.5. If I take this times that, I get this. This times this, I get that, and so forth. And when I add all these together, I get 3.5. Did I go through this computation last time in Excel? No? All right, let's do that. We'll come back to this. These are the results. I'm sorry? Send me email saying put the dice and RVs file up there. I'm going to go through this quickly in Excel. We'll get the same results. All right, well, I need to make it a little smaller here, or move it to the right a little bit. I'm going to label the top column there just by the letter X. Make it even bigger. I'm going to call this X, and I'm going to list down this column the numbers 1 through 6. I'm going to make that bold. I'm going to right justify it just so that it looks a little neater. Okay. So here I'm talking about a random variable. I'm calling it X, and the values I can observe of that random variable are 1 through 6. Now what I'm going to do is I'm going to create a column of probabilities, and I'm going to assume that what we have is a fair six-sided die. So what's the probability of a 1 is equal to 1 divided by 6. Now, that's the way you want to enter the formula or the computation of the probabilities in this case. If you don't, if you put it in an approximation Excel will detect that there's something not quite right, and it'll give you an error, if you will, saying, I'm sorry, your probabilities don't sum to 1, or something like that. Not quite exactly that. So I'm going to hit enter, and now what I'm going to do is I'm just going to drag that formula all the way down. Now what Excel is doing is it's expressing the probability here only to 5 decimal places. If I change the formatting, well, it's going to be out to, however many places I want, all right, and it will be more precise. So what we're seeing here is an approximation of what is stored internally.
Can you go back again?
Equals 1 divided by 6. That's simply the probability, if you will, of any one of these faces. All right, now, what I'm going to do next is the following, is I'm going to create a column where I take x times the probability of x. So in this column, what I'm going to do is I'm going to take this, so here will be this times that, here will be this times that, and so forth. And then down here, I'm going to sum them all together. So the way you do that, equals, you take and click on the cell containing your value of x. You enter in a asterisk to represent multiplication, and you multiply it times the probability that you observe this value. Now, because I've set this up appropriately, I can just extend the formula down, and now what I'm going to do is I'm going to sum all of that. That's 3.5. This is, I'm just going to add in some notation here, the expected value of x, in this case, is equal to 3.5. Now, suppose I roll a die 1,000 times. I add the number of dots on the top face across all those 1,000 times, and I divide by 1,000. The result will be close to 3.5. Let me demonstrate that through simulation. So what I'm going to do now is I'm going to actually roll internally in the computer a die. It's not quite this way, but good enough. We're going to roll a die 1,000 times. We're going to compute the mean value of those results. And the result should be close to 3.5. It might be a little bit bigger, it might be a little bit less, but it should be fairly close. Now what I'm going to do here is the following, is I'm going to make use of my data analysis toolkit. So in order to do that, I clicked on the tab where it said data at the top. All right, and I'm going to click on this icon over on the right where it says data analysis. Now, again, if you have a Mac, you don't have this tool. If you have a PC at home, you may not see this either because that add-in has not been added to the Excel program. If you want to know how to do that, I can talk to you after class. You can get that visible on your own computer. All right, now, I click on that icon, and I have a lot of different tools here I can use. By default, it says random number generation. That's what I want. So if I click OK there, it brings me up this dialog box. And what I'm going to do now is I'm going to roll this die 1,000 times. And the way I'm going to display it is the following. I'm going to have 10 columns and then 100 rows. So I'm going to enter in here a 10, which is basically the number of columns I'm going to generate numbers for, and this number will be the number of rows. I'm just choosing 1,000 because that's a nice choice. So I've entered a 10 and a 100. Now the type of random numbers I'm going to generate, in fact, are discrete. And what I'm going to do is I'm going to make use of these values I've created over here. And the way I make use of them is I bring my mouse to this position here. I'm going to click, it will collapse, and then I'm going to drag that over these 12 cells. All right, now, I'm going to leave this entry blank, random seed. I'm going to click on this radio button here called Output Range. And then that's going to allow me to specify where I want my results. So what I'm going to do is I'm going to put the results, let's begin in, let's put it here. So I'm going to click on this icon here. I'm going to click on 12. Now what's going to happen here is the following. I'm going to get 1,000 numbers. There will be 10 columns, all right, 100 rows, and the first result will be put in this cell right here. So to the right, 10 columns, and down 100 rows. All right. So internally inside the computer, they roll the die and got a 3. Then they roll it and got a 1. Then a 4, and a 6, a 6, a 6, a 1, a 3, and so forth. Now let's compute the mean, the sample mean, for this data. So I have, let me put down the following. I have n is equal to 1,000, so it's going to be 100. And let's compute the sample mean. Now what's the function we use for computing the sample mean? It's average. So all I need to do is type in equals AVERAGE. Oops. Without a 4. And then what I'm going to do is I'm going to drag my cursor over all those 1,000 cells. So I click and I drag it downward, and then to the right, oops, yeah, until I've captured all the cells in which I've placed the data. I have no idea what the results are going to be, but it should be close to 3.5. 3.54. Now, if you do it on your computer, you won't necessarily get the same numbers that I do. You'll simply get, some number close to 3.5. That, see, the expected value in this case of 3.5 is the theoretical value. The observed value in rolling a die 1,000 times was 3.54. If my results were a lot different from this 3.5, suppose I had a 3.0 or maybe a 2.5, what that would suggest is the die is not a fair die. Okay, one face is loaded. Now, there are actually more sophisticated statistical tests than what I've just described, but that's why we're kind of interested in this value, or this value here, the theoretical value and this. That suggests the model we're using is a reasonable model.
So if a mean x is not close to the mean male x, it means it's not a fair die.
It's not a fair die, that's correct. Now the question, I haven't really told you what close is, okay? That has to wait a little bit, all right? Now, if you roll a die 10 times, you don't have a very good sample size. Here I've done 1,000. At 1,000, we ought to get results pretty close to 3.5. All right? Now, let's go through the process of computing the variance, the theoretical variance, defined for a random variable, and see what we get there. So I think what I'll do is I'm going to skip a column here. Let's see, how do we compute that? We take every value of x, we subtract from it the mean value of x, which is also written as the expected value of x. And what am I going to do is I'm going to square that difference. So I enter in a caret followed by a 2, and then I multiply that times the probability of those values of x. So I'm taking every value. That's what I'm going to do. I'm going to take the numbers 1 through 6. And for each one of them, I'm going to subtract out the mean value, or the expected value, which is 3.5. That difference will be squared, and then that will be multiplied times the probability of that value of x. Now I'm going to right justify that, because otherwise it looks funny. Okay. Okay, so now I actually do the computation. So I take my value, my observed value of 1, which is an A2, and I subtract from that this value 3.5. Now what I'm going to do is I'm just going to enter in 3.5. I could reference this cell, but there's no value in doing that in this case. Now that difference will be squared. Now I want to multiply that times the probability of this value, which is in this cell here. Now, I can extend this formula downward, all right, and I'll get the appropriate calculation for each of the values 1 through 6. Whoops, I messed up here. What did I do?
First, you didn't count the probability, you had this.
Oh, yeah, I got the wrong one there. I'm sorry, okay. So we're going to undo all of this. Yeah, I didn't have this. It's not supposed to be C2. It's supposed to be B2. Okay, that's, yeah, B2 is the probability here. Now, if I extend that downward, oops, one more. In this case, these are going to be the same, these are going to be the same, and these will be the same. That's just for this example here. All right, now, the variance then is the sum of this column. Well, let's do that. And I'm going to just type in, say that's equal to the variance of x. Oh, I know. It doesn't like the fact that I have entered in what it thinks is a formula, and I wanted it to interpret it as simply a text, and it still has not figured that out. So will I just go like that? That's the variance of x. What's the standard deviation of x? It's nothing more than the square root of that. So I'm going to equals SQRT, square root of this value, and that's nothing more than the standard deviation of x. So this is my sigma squared, that's my sigma. All right, now, let's determine the sample standard deviation. For this data here. It should be pretty close to this value right here. What's the name of the function that I use to compute the standard deviation? STDEV.S. STDEV.S. You want S because it's going to compute a sample standard deviation. All right, now, again, I'm just going to select all these cells. All right, so I have the cells, in my case, are A12 through J111. Again, if I should get a result that's pretty close to this here. I get 1.75313. That's pretty close. Again, close, I can't really define that right at this moment. In fact, even that's close in terms of standard deviations. It's not a trivial calculation, but that's pretty close. All right. So it looks as though, again, this die is a fair die. All right. The way in which the computer generates these numbers seems to be pretty consistent with the idea of rolling a die. Now, if you do the same thing, these values, the theoretical value, the expected value of x, the variance of x, the standard deviation of x, those should be the same. The results that you get for the sample mean and the sample standard deviation, they should be a little different. Every time you redo this, the results should be slightly different. Okay. I will put that up on the class webpage. What I've done here in this file is I've just shown the same computations. The computation of the expected value of x and the computation of the variance. Those numbers are the same as what I had in Excel. And down below here, I created this is the rules for means, and I went through the computations. These results here are consistent with those rules, if you were to check that out. Okay, you can verify that fact. So this file was invented for other reasons. Okay, we'll come back to, and here, if we sum the top face of two dice and call that W, the mean is simply the sum of 3.5 and 3.5. And the variance is twice the value I have up there. All right, so these are kind of the final results if you will, of the calculations. And it's just an illustration of not only the computation of the expected value and the variance for a single roll of a die, and then applying it those rules. All right, let's see. This was the punchline to show that the sample mean should be approximately equal to the theoretical. The standard deviation is often denoted with a capital S, capital D, and the particular random variable that we are referring to is placed in the parentheses. Or we might write the letter sigma with a subscript of x. Continuous random variables have means and variances defined using techniques of calculus. So the only reason we don't do that is there's no assumption that you've had any calculus here. You want to be a statistician, that's what you do is you study a fair amount of math to do that. Okay. Chapter 16 will be included, all right, on the exam next week. Now, I'll spend the first half hour next week addressing last-minute questions. We'll have about, about 2 hours for the exam, which is what I've done before. And then following that, we'll continue with the lecture. Today, we should finish 17 and actually start 18 a little bit too. All right? Just to kind of whet your appetite on statistical inference. Okay.
In chapter 15, are you going to test the Bay rule?
I don't use, I don't think I assigned any problems involving Bayes' rule.
Because you teach it in the class, but the rule is Sunday.
I know. Think of it, you got bonus material. You didn't have to pay for it, and you still got it. Yes.
This stuff seems a little more complex than a lot of the stuff that we've been working on. What kind of question would you ask on the test in terms of this? Like,
Well, remember.
Just kind of plug, like you're going to give us.
Yeah, if you look at the homework in 16, a couple of those problems are compute the mean, compute the standard deviation, compute the variance, which I've just illustrated. Some of them are apply the rules that I gave you. So, you know, when I make up an exam, that's what I often look. I look at the homework. Now, the example exams I have from 2012, you might have to look in the final to see problems appropriate for all these chapters, because I don't cover exactly the same amount on a given exam from quarter to quarter. But those are, you know, the examples that I have in the exam. The example examples are typical of what, you know, I usually ask similar sorts of problems. Now, if you, in I think exam 2, there may not be a lot on random variables, but that may be because that quarter I gave the exam a little earlier, okay? But so you might have to look in the final to look at, you know, problems appropriate for maybe 15 and 16.
And is the final just going to be over the stuff that you cover at the end?
Well, usually most questions on the final are from the chapters I have not quizzed you on, so it'd be 17 through 21, or sometimes I'll have an extra credit on 22, but that's typically what I do on the final. Now what I also do, however, is I often will pick problems that I did not, or I will pick problems associated with prior topics that I had not previously quizzed you on. So I think all the exams, if you look at all the exams and all the problems, it's pretty representative of the types of questions I'm going to ask you on all the exams, but sometimes I shift them from one spot to another. Okay? Now, to understand 17 through 21, you need to understand random variables. Okay? To understand random variables, you need to know probability. That's why I do the quiz on 11 and 14 right away, or, that's why I focus on it. I will have questions on 12 and 13, which involve experiments, observations, and questions on 8 and 9, which involve linear regression. Now, in the exam 1, I said, one problem was, okay, here's some data, create a scatter plot. In chapter 8, what I do basically is say, here's the scatter plot, here's the equation, now graph the line, the regression line. So 8 kind of assumes knowledge of 7, but I won't ask you, I'd ask you questions on this next exam, typical of what you would find in the homework for chapter 8. Same for chapter 9. I'll look in there and say, what sorts of questions did I ask there? And then replicate some of those on the exam next week. Okay. Let's see here. I think what we should do is we should cover maybe one or two more slides and then take a break. Okay? What we're going to do next, all right, is we're going to talk about, we can describe it in several ways. A binomial experiment, and closely related, a binomial random variable. Now, there are lots of experiments out there, but this is a type of experiment that we can analyze now at this point, and in fact, we make use of in statistics. Now, when I use the word binomial experiment, this is what I mean. All these conditions here are met. If one of these conditions is not met, it's not a binomial experiment. It may be a very interesting experiment, but it's not a binomial experiment. When you think binomial experiment, think of tossing a coin. I guess I'm broke today. I don't have any coins. When you flip a coin, all right, you can either have a head or a tail. And typically, when we talk about a binomial experiment, we are doing that repeatedly. Okay. So when I use the expression binomial experiment, these conditions hold. I have n observations or trials. When I flip a coin, I can think of that as an observation, or we also use the term trial. N is some positive integer. It could be small as 1. That's pretty rare because it's not a very interesting case. But 2, 3, 5, there's a fixed number. I toss a coin 100 times. That means n is equal to 100. Now, each observation or trial is independent of the others. When I flip a coin, what happens on the 5th toss doesn't influence anything subsequent, or is not influenced by anything prior. They're all independent. Each observation falls into one or two categories. Something we call success, something we call failure. Now, when I flip a coin, I could decide to use head as success, or I could use tail as success.
So only two options, right?
Two. Each observation falls into one of two categories. Something I call success, and something I call failure. All right, now, the last assumption that we make for a binomial experiment is the probability of success is the same in each trial. When I flip a coin, all right, the probability of a head remains the same from trial to trial. Now we could have, in fact, we don't have to have coin tossing to illustrate these ideas. Let me give you another example here. I'm going to roll a die. I'll assume it's a fair six-sided die 50 times. So what I'm saying is n is equal to 50. And I'm going to just say success is observing a result which is divisible by 3. Failure would be anything else. A 1, a 2, a 4, or a 5. Now, the probability of success is often denoted by a small letter p. There are 2 outcomes that constitute success out of a total of 6 in a single roll. So the probability of success in a given roll is 2 out of 6, or 1/3. The probability of failure is actually 1 minus that. We often represent the probability of failure by Q, again, which is equal to 1 minus P, and that's 2/3. So this is the binomial experiment. I'm doing it 50 times. The observations or the trials are independent. I have something I call success, something I call failure. And the probability of success remains the same on each time. Now this was just one choice here of success and failure. There's nothing wrong with the numbers 1, 2, 4, and 5. Calling them a failure is simply an arbitrary choice. Sometimes what we have is we have a situation where dying is considered success. There's no normative judgment associated with the word success as I use it in this class. It's just one of the possible outcomes, or an outcome on a given trial. Okay, now, what we are interested in is the following. And we'll take a break with this once I write this down. I'm going to use the letter X to represent the number of successes in 50 trials. Now, what are the possible observed values X? X is a random variable as the count of the number of successes. The smallest one is 0. That's very unlikely, but you could have 0 successes, even in a fair die. You could have 1 success. You could have 2, 3, and so forth, on up to 50. Those are the only observations we can make in this case. No other possibilities can be observed. X is a random variable. I'm going to show you how to compute the probabilities associated with every one of these values here. You can compute the expected value of X. It turns out there's a nice little theorem that says there's a really easy way of computing it for binomial experiments. In this case, it would be 50 n times 1/3. That's the expected value. Turns out that the variance in these cases is easy to compute as well. There's a theorem that says the variance of X will be n 50 times 1/3 times 2/3. N times P times Q. Nice little result in statistics or in probability. We can prove it. I'm simply going to state it. Okay, now. So this is an example of a binomial experiment. And if I let X represent the number of successes in 50 trials, what I would say is that X has a binomial distribution. A binomial distribution, if X has a binomial distribution, meaning I can compute the probabilities associated with the numbers 0 through 50 from a formula, and what I would do is the following. I would say X is a random variable which has, tilde, has a binomial distribution. We're going to have a regular, precise formula for computing probabilities, where the number of trials I have is 50, and the probability of success is 1/3. This is my value of N, this is my value of P. Okay, let's take a break for about 10 minutes this time around, and when we come back, we'll talk more about the details here.
The B is binomial distribution.
B is a symbol for binomial.
It's binomial. X to B is binomial.
X has, tilde means X has a binomial distribution.